Today we will be talking about optimization in genetics. Sickle cell anemia is an inherited blood disease caused by one single mutation. Individuals who are homozygous for the recessive gene have the disease. Today in our optimization problem, we will use these variables. 2n equals the number of chromosomes. Lowercase p equals the frequency of uppercase A allele. Uppercase p equals the frequency of uppercase A genotype. Q equals the frequency of lowercase a allele. R equals frequency of lowercase a genotype, and uppercase Q equals the frequency of uppercase A genotype. First, we show that the allele frequencies of lowercase p and q can be expressed by the equations lowercase p equals uppercase p plus 1/2 uppercase q, and lowercase q equals 1/2 uppercase q plus r. The appropriate numbers to plug in for the variables can easily be calculated by creating a Punnett square. In this way, it can be seen that the frequency of the uppercase A genotype is 0.5. The frequency of the uppercase A genotype is 0.5, and the frequency of the lowercase a genotype is 0. When the numbers are plugged into the equations, lowercase p, the frequency of the uppercase A allele is 0.75, and lowercase q, the frequency of the lowercase a allele is 0.25. This is also seen in the genotypes that are being crossed. 0.75 of those alleles are uppercase A, and 0.25 of those alleles are lowercase a. We were then able to prove that the frequency of all chromosomes is 100% when the frequency of the uppercase A and lowercase a equal 1. The equation p squared plus 2pq plus q squared represents every possible genotype. P squared is uppercase A homozygous dominant, 2pq is uppercase A heterozygous, and q squared is lowercase a homozygous dominant. We plugged in the appropriate values into the equation and accurately got a frequency of 1 or 100%.
For step 3, in a situation where the heterozygous genotype A lowercase a has a survival advantage, we first have to look at the probabilities of mating that are given to us, which are, for A lowercase a, the probability of mating is 0.8, while lowercase a probability of mating is 0.2, and the heterozygous one is A lowercase a probability of mating, which is 100%. Based off of the original equation that we found of f of p, which gives us our probabilities, we now establish a new balance equation of f of p, where we use the probabilities that were given to us in our f of p equation and plug in what we originally solved for, which was 0.75 for our p value and 0.25 for our q value. Our new balance equation is as shown as f of p equals 0.8 multiplied by the probability of our q value squared, plus 2 times our p and q value, plus 0.2 times the probability that we got for our q value squared. After solving this equation, we end up with a value of 0.8375. The heterozygous A lowercase a now has a survival advantage in this situation, as they are said to not have sickle cell anemia and have a higher resistance to malaria. This is due to having a different genetic values of both GAG and GTG present on the chromosome, which is why we end up getting new values, especially when there are new probabilities of mating and frequencies for those probabilities to show up. For step 4, we want to solve for a max value of p where the heterozygous genotype A lowercase a has the largest survival advantage in their lifespan of where they develop from an egg and what happens to their genotype when they develop into an adult. We want to use the 0.8375 value from the previous equation, from our balance equation, and set it equal to the same f of p equation like so. you will do 0.8375 equal to that same balance equation and the same frequency that we used for our Q value of 0.25 and only solve for the variable P. After doing so, we end up using the quadratic formula to solve and get two values of P, those of which include a positive and a negative. The positive value of 0.75 makes sense in this case, and the negative value of 1.375 would not make sense. Thus, the frequency of the allele in the adult population is still 0.75. The same value of the frequency 0.75 is valid because a person's genetic makeup of alleles doesn't change from when you were an egg and fertilized to when you become an adult. This is shown by the chart below as your average genotype value. This is shown by the chart below as your genotype doesn't change. There is only a possibility of the probability or frequency of that allele being passed down onto different generations as they reproduce. Note that the frequency of the allele A, capital A, in the adult population is the same as the frequency as it was in the egg population.
As we determined earlier, P plus Q equals 1, and we were given the balance equation as f of P equals 0.8 P squared plus 1 times P times Q plus 0.2 Q squared. With plugging in 0.75 for P and 0.25 for Q, we get a value of 0.8375. As we plugged in the value of P of 0.75 to the new balance equation of 1 minus 0.2 P squared minus 0.8 times 1 minus P squared, we also get the value of 0.8375. The probability of reproduction is dependent on the genotype, and in this case, there is an advantage of the heterozygous genotype. As generations continue to succeed, the allele frequency of P continues to move towards a local maximum of the function of f. Next, we had to figure out what value of P maximizes the function. As we use the equation f of P equals 1 minus 0.2 P squared minus 0.8 1 minus P squared, we combined all like terms and finally took the derivative of the function negative P squared plus 1.6 P plus 0.2, which gives us the derivative of f of P equal to negative 2P plus 0.16. We then set it equal to 0 and determined the value of P as 0.8. In order to make sure and prove that this was the highest possible frequency this genotype could achieve in terms of having a survival advantage, we did a first derivative test. Now we are generalizing work for general heterozygous advantages. We are to assume that there's a slight disadvantage for capital A, which gives us the probability being 1 plus S1 is greater than or equal to 0. And then there's also a slight disadvantage for lowercase a, with the probability being 1 plus S2 greater than or equal to 0. And lastly, we assume the heterozygous genotype of capital A, lowercase a, always produces with the probability being equal to 1. We can see this in the equation 1 plus S1 P squared plus S2 times 1 minus P squared. We then combine like terms to get the equation of 1 plus S1 P squared plus S2 P squared minus 2 S2P plus S2. In order for us to find the derivative, after setting the derivative equal to 0, factoring out the 2, and isolating P, we find the value of P to equal S2 divided by S1 plus S2, which concludes it's the maximum of the function f of P.
Then we had to show that the function of P is equal to 1 plus S1 times S2 divided by S1 plus S2 is less than 1. Both S1 and S2 will be negative numbers because there's a slight disadvantage in matching. Thus, when you multiply two negative numbers together, you get an overall positive number. And a negative number plus a negative number is again a negative number. When you divide a positive number by a negative number, you get an overall negative number. And 1 plus a negative number is a number less than 1. Finally, we use this information here. P0 is equal to the uppercase A allele frequency in the first generation. The uppercase A allele frequency plus the lowercase a allele is equal to 1. So we were then able to solve for the lowercase a allele frequency, which is 1 minus the frequency of the uppercase A frequency. So the homozygous uppercase A genotype frequency is equal to P0 squared, and the homozygous recessive lowercase a genotype frequency is equal to Q0 squared. We were then able to show that the frequency of the uppercase A allele in the adult population after selection is equal to P1 equals 1 plus S1 times P to the 0 squared plus P0 times 1 minus P0 all over the function of P0. We were able to find this by finding the frequencies of each genotype: the homozygous dominant, homozygous recessive, and the heterozygous. Because we were just trying to find the genotype frequency of the uppercase allele, we only had to use the homozygous for the uppercase genotype frequency and the heterozygous in order to find that this fraction was true. This equate function was true. So thus we use this equation for the frequency of the homozygous uppercase A genotype frequency, which can be found here, plus half of the frequency for the heterozygous uppercase lowercase a genotype frequency, seen here, all over the function of P0. We only used half because there is only one uppercase A allele, and thus we only needed half of this equation. And that is how we found it.